so I'm going to get to it. Is this dry erase properly? Yuck. That is awful. Who did this? That's the flip chart marker. There's the problem right there. That's the wrong marker. There we go. That's better. These are the wrong markers. That's dangerous. Okay, so I think I'm ready to get started. So we are here. Hello. I'm Zebulon, Vitruvius, Pike, and this is my presentation on the Victorian history of spacecraft. Now, if you're a writer or a game player or an author or something like that, there's lots of ways to get into space. And I've found that it's useful to know, well, when you're doing steampunk, steampunk comes with a lot of baggage because the 19th century, it happened. And they had certain ideas about how things were going to work. So if you don't take that into account when you're creating your world or trying to write your story, you're going to miss things and people are going to go, hey, that's not steampunk or whatever. So what I like to do, I like to go through the history of the Victorian era and how they got into space, or at least how they thought they were going to be getting into space. There's two ways of doing that when you're a writer. One is to go through the science of it, to really work out how things work. And the other way is just make crap up. Jules Verne is an example of going through the science of things. Sometimes the science was wrong, but he paid a lot of attention to the science of the day when he created his spacecraft, when he created Nautilus, when he went to the center of the Earth. He paid a lot of attention to that. H.G. Wells was of the other category. He wasn't concerned with how you got there or the science of it. He was telling a different story. He was telling a social story. Jules Verne kind of hated H.G. Wells for that. He just made stuff up. Steampunk can do both of those things. Let's see, where do we want to do? Let's start with something early. This is one of the early science fiction stories called The Unparalleled Adventure of One Hans Pfaall, written by Edgar Allan Poe in 1835. So this is a pretty early science fiction story. And one of his, basically the idea is this character is going to go to the moon. Well, in the 1830s, how did you fly? You flew in a balloon. So Hans Pfaall's ship was kind of an upside down cap, you know, like the little gnome caps, was kind of upside down and filled with a gas. What did he call it? It's 100 feet long, 30 feet in diameter, 40,000 cubic feet of gas. Now, just to put that in perspective, you know how big the Goodyear blimp is. His balloon was like half that size. Let's see, a gas to be formed from these later materials, a gas never yet generated by any other person than myself, or at least never applied to any similar purpose. I can only venture to say here that is a consistent of nitrogen, so long considered irreducible, and that its density is about 37.5 times less that of hydrogen. So basically, he's taking hydrogen and breaking it down into its constituent atoms so that it's an even lighter gas than hydrogen. We're going to talk about that a little more later. But even then, you know how balloons work. That's not going to get you to the moon. You need a little more oomph. So his plan, good old Hans Pfaall's plan, was dig a hole and fill it with explosives. So he's going to have this big explosion, throw himself up to the moon. Well, when it's time to go, when it's time for him to leave, his creditors arrive. They're kind of upset because he hasn't been paying them back for the money he borrowed. So they're all down here, you know, yelling at him when the explosion goes off, and it kills all his creditors and propels him to the moon, where he comes back 3 years later with Dunarians? I forget what he called them. People from the moon. He comes back. Now, this story was presented in a paper, in a newspaper, as if it were a narrative, as if Edgar Allan Poe was writing a news story. And only at the very end did he say, oh yeah, by the way, I made all this crap up. But I guess at the time it was fairly plausible that you could do this. So balloons. Balloons are popular. Let's move on to something else. 1865, Jules Verne, From the Earth to the Moon. The Columbiad. Now the Columbiad, completely different mechanism. The men of the Baltimore Gun Club built a cannon in Florida. It was 9 feet in diameter, 180 feet deep, or no, the barrel was 900 feet, and the 180 feet of the bottom was filled with 400,000 pounds of gun cotton. So you have all your explosives down here, and then you take your projectile and you sit it in there, and you get your guys inside, and you wait for the moon to be in the right place, and you set it off. So you're going to the moon. Now, the muzzle velocity, let's see, what did they give the muzzle velocity for? Muzzle velocity of 12,000 yards per second. Now that's a recalculated value. Jules Verne had made a mistake in his calculations, so what he published was a velocity that was much lower that would not be sufficient to get him to the moon. But, if he did his math right, 12,000 yards per second to get him to the moon. Now, you've got like 800 feet of barrel to go from 0 to that velocity.
There's some issues with that acceleration.
There are some issues with that acceleration. Let's put that into perspective. A roller coaster. You've all ridden a roller coaster, right? Roller coasters tend to run no more than 3 or 4 Gs. Okay, so we're in 1 G of acceleration here. 3 or 4 times that is the maximum you'll get on a roller coaster. The space shuttle, when it launches, it goes at under 3 Gs. It's a nice, slow acceleration. At from 4 to 6 Gs, you'll black out unless you have like a special suit that squeezes the blood out of your legs back into your head. Okay, inflatable pants keep you from passing out. That's at 4 to 6 Gs. Fighter pilots can sustain 8 Gs for a short period of time. There's been some high velocity experiments where humans can survive some really high, accelerations, but not much higher than that. At 30 to 35 Gs of acceleration, it'll break your ribs. At 70 to 100 Gs, the acceleration will tear the aorta right out of your heart. The acceleration of this is, well, calculate Konstantin Tsiolkovsky, and I'll mention him later because he's a really cool guy. He calculated that acceleration would be 22,000 Gs. Okay? The human body becomes chunky salsa at those accelerations. Now, this doesn't keep today people thinking about using a gun to get things into space, because it's pretty darn cheap to set off all these explosives and let the acceleration take it. But you have to build something that can withstand 22,000 Gs of acceleration. And even a lot of modern electronics, they have trouble with that. Let's see. 1, 2, 9, 9. Now let's talk again about Konstantin Tsiolkovsky. Tsiolkovsky was a Russian mathematician. And he taught his students this idea. So we start with the Eiffel Tower. Okay. The Eiffel Tower, the top of the Eiffel Tower is moving pretty fast relative to the Earth because it's further away and it's connected. If you were to make the Eiffel Tower taller, this would be moving pretty fast. And at some point, if you made it even taller, it would be at orbital velocity. You understand how orbital velocity works? Basically, here's a quick introduction to orbital velocity. If I take a cannon or a baseball or something, I throw it, it's going to go so far and then fall. If I throw it faster, it'll go further before it falls, before it gets to the ground. Well, if I get it faster still, eventually it'll be going fast enough. It'll fall as fast as it's going tangentially, and it won't hit the ground. It'll fall but miss. Okay, that's what free fall is all about. So if you have a big tower like this, at orbital velocity, you could just take your satellite and just push it out a window, and it's already at orbital velocity. Now this tower, this point here, is at 21,000 miles. So Tsiolkovsky's space elevator, which basically you just, ride the elevator up to the top, have to be kind of tall. The Eiffel Tower was 1,000 feet tall, weighing in at 10,000 tons. If we were to take that up to 21,000 miles, it'd be 110,000 times taller and over 1 trillion tons. That's assuming that we're just making it taller and not wider to support all that weight. But of course, you don't have that weight.
And it's made of steel.
If it was made of iron.
Ah.
It was iron, it's not steel. They have to really take care of it too to keep it from falling down. So this is another thing that's not going to work. But the thing is, remember, Tsiolkovsky was a math teacher. He wasn't proposing building a space elevator as a way to get up into space. He was using this as a teaching mechanism to explain how orbits worked. Because he had other plans for getting into space. And we will come back to that later. Tsiolkovsky comes up numerous times. In 1869, Edward Everett Hale published a story in Atlantic Monthly called The Brick Moon. Now here's the idea. You know how to navigate by the stars, basically, right? North Pole, North Star, certain stars, if they're overhead, that'll tell you your latitude, north and south. It's easy. But longitude, how far east or west you are, is very difficult. You need tables, and you need an accurate clock to be able to do that. Well, what if we made it that simple, like the North Star? If we just had a fixed point in the sky that you could look up and say, okay, this is at that angle, here's my longitude. So the idea is to build a brick moon. Just build a sphere out of bricks. Bricks are cheap, bricks are easy, they can take a lot of heat, you can just paint them. So we're going to put this up in the sky. We're going to put several of them up in the sky. We're going to put it up in the sky. It'll be at a certain place, and then you just look up and say, okay, this is at that angle. I know where I am. It's a GPS satellite. It is literally a GPS satellite. Except instead of it telling you where you are, you figure out where you are by looking at it. So in this story, he's got to get this thing up into the sky. You got to throw this thing up into the sky. How are you going to do this? How big was it? 200 feet in diameter. Man, this thing 200 feet in diameter. How are you going to get that up in the sky? Well, he had this idea. Oh, they shouldn't be touching, should they? We're going to do this again. Give me a little illustration here, and that. So we're going to have two gigantic flywheels. And we're going to start spinning these things up. So we're going to get this one spinning this direction, and this one spinning this direction. We got a stream nearby that's running a water wheel that just starts spinning these big wheels up. Spinning, 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 faster and faster. Just keep adding more and more energy. And because they're big and they're heavy, they have all this energy. And then we just build a ramp, and we have our moon here, and we're just going to roll this down the hill. It's going to roll between these wheels. It could go wham and throw that right up. This is, you know, the tennis ball throwers.
Or baseball.
Or baseball. This is exactly what that is. But this is 1869, and he's going to take this 200-foot sphere
of brick
and throw it up into the sky. Well, it's a dark and stormy night, and it's raining, and the workers who are building this sphere, they happen to be inside, out of the rain. When the mud collapses and it falls and it gets thrown up into the sky with, you know, the group of workers and their families up in the sky in this moon.
Oh, it's hollow.
It's hollow.
They're in it.
Yeah,
Okay.
they're in it. It's not a solid brick thing. It's actually built with like Gothic architecture with all these arches and things to help support it. Imagine like a 20-sided die with all the supports inside. Very, very, very neat. So now you've got these people up in space. And they try to figure out how to communicate with them. And the way they do that is all the people go out onto the surface. Yeah, they're not paying much attention to the fact that there's no air up there, but all the people go out on the surface. They all get together in a group and they jump in Morse code. So people with telescopes can see just enough motion that they can tell. Now, you have to recognize that, again, a lot of science fiction is not written about the science. He's not necessarily proposing that this is how it's going to work. But like Jules Verne, he spends a lot of time on the math of how this would work. He's wrong, of course, but he spends a lot of time on that. But what he's really talking about is this society that exists up here that is isolated from us, yet still communicates with us, living in these conditions. He like builds up this kind of society and talks about human nature and the way people behave and politics. You know, independent, they become an independent nation of like 30 families or something like that.
Reminds me of a Futurama episode.
I didn't see that. I didn't see a lot of Futurama, but probably. Now, by far, the most common method in the 19th century, and there's lots of different things, but the most common method that was used in the 19th century for getting into space was anti-gravity. You think of that as kind of a modern thing, but no, in the 19th century, that was the way. Most of the stories that talked about spaceships going up into space used some form of anti-gravity. One of the first ones was Orrin Lindsay's Plan for Aerial Navigation by John Leonard Riddle in 1847. Now, something to understand about gravity and what people thought of gravity at the time. Remember, we're starting to learn science, how things work, and we understand about light. Light is a wave. We understand that light can be broken down into waves. So, and electricity is also that way. So they were thinking that gravity was likely to be something similar, like a light wave. So if you were to take a sphere, for that matter, he called it a magnetic balloon. And you use the right materials, just like something that is opaque doesn't let the light in. If you could make this opaque to gravity, it wouldn't let the gravity in. And therefore it would float. Just like a balloon. If you take the air or put a lighter air in a balloon, it floats on the other air. It seemed perfectly reasonable. And if you read the literature of the day, that's how they were doing it. So variations on this, well, how do you then move this thing around? So you've got this sphere made out of some magical material that's impervious to gravity. So you put some windows in it. You open a window, you let a little bit of gravity in, and then, it'll pull you this way. You close that window, you open a window on the other side, it'll let gravity in on the other side, and it'll pull you that way. So he wrote this story of traveling around with this balloon, this 10-foot diameter sphere. Let's see. It took him, 10 days of provisions, bottles of wine, one of brandy, 2.5 days to go to the moon. That's how he figured it out. He would go to the moon in 2.5 days. And he came back. Now here's an interesting thing. When he came back, he was coming back pretty fast because the Earth has a lot of gravity to pull you towards it. So he skipped off the atmosphere to help slow himself down. We do that. Apollo did that all the time. You skip off the atmosphere to slow yourself down, and then you come in. Again, this is one of those stories that's kind of the opposite. Okay, this is much more like Tsiolkovsky's story, where he's using this as an explanation of how science works, how gravity works. His story was 10 pages long, and an additional 5 pages of footnotes. Okay, so the footnotes were half, again, as much as the story was, because that's what he was talking about. He was talking about how gravity works. Now, if you've read some science fiction, have you read H.G. Wells' First Men in the Moon? You read First Men in the Moon? H.G. Wells used exactly this. Only his character called it the substance that he made this out of that was opaque to light as cavorite, because the guy's name who invented it was Cavor. Cavor? Cavor. I've heard it pronounced differently. I think I saw a BBC production, a fairly recent BBC production. I think they called him Cavor. But he had a different idea. He understood a little differently how gravity worked and how we work within gravity. So here we are, standing on the Earth, and the Earth is spinning at 1,000 miles an hour. Well, at the equator, it would be 1,000 miles an hour. In England, where the story was written, it was like 600 or 700 miles an hour. Okay, so you're going 700 miles an hour, but that's because you're held down by gravity. What would happen if you closed all the windows on your cavorite sphere and now became impervious to gravity? What would happen? Well, if the Earth is spinning at 700 miles an hour, you have 700 miles an hour velocity, and you're going to go at 700 miles an hour. Suddenly, boom! Now in the story, he has them going straight up. But that's not what's going to happen, because you're traveling tangentially. You're going in this direction, because that's the way the Earth is spinning. So 700 miles an hour, and you're going to be going. Now, from the ground perspective, it's only going to look like 100 miles an hour. You know, from this perspective, it's going to look like you're going up at 100 miles an hour. But still, that's going to be pretty impressive. And he does that in his story. He has his spacecraft blow through the roof and go up into space. Actually, before that, he has a test plate. He builds a plate of cavorite. Now, the way this works, remember, it's opaque to gravity. Okay, so gravity is like a shadow. So let's do it this way. So we've got the Earth and we've got our plate. So there is a shadow here. So everything in this shadow is now isolated from the gravity of the Earth. So all this column of air, all the way up for 100 miles, now is no longer weighed down by its own weight of gravity. So it's going to rush up at 700 miles an hour. And then it's going to leave a vacuum here, where this air is going to rush into the shadow and rush up. In his story, he was afraid that if he had bolted that plate down to the ground, instead of allowing it to fly free, he would have destroyed the Earth. All the atmosphere would have been squirted up into space.
What about the resulting hurricane?
Well, yeah, everything else would have been, sucked up and all that other stuff too. Now, there's a problem with this. Can anyone see the problem with that? Whether that would work or not? Again, we're talking about a shadow. If this, you got gravity over here. The Earth, all of it produces gravity. So even though when you're doing math, you can treat it like a point, this part has gravity, which means it is able to pull on the air up here. Not as much, but it's going to be there. So basically what you would get is you would have the shadow, and the air would try to rush up. But it wouldn't rush up quite so much because this air would be affected by gravity still, because it's not in the shadow, or as much of a shadow. So you would get like a little wind effect down at the bottom, which would be cool. Yeah, it's a genius turning that into a perpetual motion machine. That's great, but it's not going to evacuate the atmosphere. By the way, this is 1899. The First Men in the Moon was written 1899. More anti-gravity. I'm going to mention Edison's Conquest of Mars. Now, if you've read War of the Worlds, the Martians come, they have big cannons, like Jules Verne's cannons, to fire their cylinders at the Earth. So when Garrett Serviss steals a sequel to War of the Worlds, he's got Thomas Edison. Edison, of course, is a genius, and he's going to create these anti-gravity things with electricity. He doesn't explain it much, but he spends $25 billion, and this is $25 billion in 1900, to build these ships to travel to Mars and beat the Martians. Now, I'm going to do a presentation on War of the Worlds, and I'm going to talk more about Garrett Serviss and his Martians and what he did with them tomorrow. But suffice it to say, H.G. Wells refused to go to the United States to sue Garrett Serviss for stealing his story, because he didn't want to give him that much credit. And I've read that story. It's not a very good story. Robert William Cole. Because I know I've got a, I'm on track here. Robert William Cole, The Struggle for Empire. This is written in 1900, set in the year 2236. Way far in the future. Right? But everything was pretty much the same. And his spacecraft were electric anti-gravity. Turn on the machine and it affects gravity. These were the origins of some of the first cigar-shaped spacecraft. You saw them in the 50s and the 60s. Craft that were, put some gun ports on it and put that in and have some ray guns, and there you go. And you powered by electricity. Anyone watch a lot of anime? You know, in anime, there's a trope within anime where you've got the male protagonist and you've got the female protagonist that you know is going to get with him. And then there's the other female protagonist who you know really should be with him. Okay, Tenchi is famous for that. He should have been with Ryoka. He really should have been. Well, he uses that same trope in here, where he's got the male protagonist, he's got this woman at home, he's going to get married and all this other stuff. He goes off with the woman's father or uncle or something to impress her, to show off how wonderful he is to her. And he ends up getting in this space battle off the shoulder in Jupiter or something like that with these aliens that came. And he gets shot down and lands on this colony and meets this girl. And then you don't hear about the woman at home anymore. Literally. She does not appear in the story at all. She's just forgotten. Not even mentioned as, well, I had this woman at home that I was going to marry, but no, I'm staying here. No, gone. Gone. Completely gone. Very much like that. His story was really about racism and American imperialism and manifest destiny and how wonderful we are. Let me see. I think I've gotten a little out of order. All right, we'll figure this out. Okay. So, this was the 19th century. This is how they were getting up into space in the 19th century. Does anyone recognize something that's missing from these narratives, from these stories?
Air?
What's that?
Air?
Air? No. No, as a mechanism to get into space. We think of steampunk and space and all these other things. How do we get up into space? How do we get up into space? Rockets. Nobody was writing about rockets. We've discovered that rockets are the way to get into space. That's the only decent way we've got to get into space. Why in the 19th century wasn't anyone writing about rockets?
You didn't have good ones?
Yeah.
And
they didn't have good ones.
And anti-gravity makes more sense.
Anti-gravity makes more sense. It's a good, because you've got the problem solved. Let's talk about rockets. They weren't completely forgotten. 1779. So basically, it's a simple design. And the illustration from 1779 looks a lot like this. So you take your inflammable air, and then you take your dephlogisticated air, L-O-G-I-S-T-I-C-A-T-U-D. You take your inflammable air and your dephlogisticated air, and you mix them together and ignite them, and you've got thrust. All right, so what are we talking about? We're talking about hydrogen and oxygen. Now, you know anything about dephlogisticated is one of my favorite words. Have you heard of the Phlogiston Theory? Phlogiston was basically a concept of when things burn, it is the phlogiston, or whatever this material is, coming out of the object. So if I have a piece of wood, there's phlogiston in there. And when it burns, when it gets hot enough, that phlogiston comes out in flames. And what you have left has been dephlogisticated. That ash is dephlogisticated, which is a great term. Well, it turns out that doesn't work, because if you take a piece of wood and you burn it and you weigh what you've got left, it's actually heavier than what you started with. People didn't understand why that was, but it was obviously not phlogiston. Their idea of phlogiston as something leaving it didn't work anymore. It's because when things burn, you've got carbon dioxide, it's sucking up the oxygen, combining, you know, all that chemistry stuff. That's why it gets heavier. But what we're dealing with here is hydrogen and oxygen, feeding it into a chamber and igniting it. It's a rocket engine. This is a liquid oxygen, a liquid fuel rocket engine, 1779, by Erasmus Darwin, Charles Darwin's grandfather. He was thinking about rocket engines, and he had figured out that this was probably one of the best rocket engines you could have. But they just didn't have the technology to do it. They could not liquefy. I mean, you know, you could use just air, hydrogen, and oxygen, but to really make it work, you'd need to liquefy it. He understood that if you make something cold, it'll liquefy, but they just didn't have the technology to refrigerate this down to the point. But he knew. He knew. Now we come up to 1883, and we've got good old Konstantin Tsiolkovsky again, writing a book called Free Space. He's got the same sort of thing. He's got himself a rocket engine. And he's got his oxygen, and he's got his hydrogen. And they know how to do this. But he's not just making a rocket engine. He's got himself an airlock. He's got little jets on the outside to help control his flight. He's got, let's see, what else? He's got plants. He's got some plants in here to provide air for the crew. He's got a real spaceship. Nobody listened to him, though, because he was kind of in Siberia at the time. A math teacher in Siberia. What does he know? But he knew. He saw how this was going to happen.
He's got a lot of free time.
He's got a lot of free time. And his basic concept designs were what became the rockets we know. Wernher von Braun knew about Konstantin Tsiolkovsky, read his book, and built his spaceships based on that. So that's where rocketry was. So for most of the 19th century, rocketry, well, it sucked. You had solid fuel, you didn't have liquid fuel, they were crap. So people didn't think about using them to get into space because they were crappy weapons of war. Not just weapons of war, but crappy weapons of war. No one liked rockets. It took that technology leap of the liquid fuel to really make that step. And I see that again and again. That's something, if you're a writer, you want to keep in mind. If you're a writer creating these worlds, it's those technological leaps. And usually it's a materials technology. They understood hydrogen, they understood oxygen, they understood rocket engines. They just didn't have the technology to make it cold enough. They understood how to build a rocket, but they just didn't have the technology, the materials technology, to make it light enough and strong enough at the same time. So keep that in mind. Something else that I want to talk about, and this is something that is so very steampunk, but that wasn't actually part of the 19th century. And it's the ether. We think of the ether, you know, ether this and ether that, ether spacecrafts, ships flying through the ether. You've got games that use it. Space 1889 is a great game. And by the way, if you want to read about the ether, this is great. There's a great chapter, oh, excuse me. And their newest edition has an even better chapter on what the ether is and how it works. Well, what is the ether and how it works? So we're going to go back to that Hans Pfaall thing and Edgar Allan Poe as a like hydrogen, breaking down hydrogen or nitrogen into its component parts. you know what the periodic table looks like, right? So you got a bunch of stuff here, you got a bunch of stuff here, you've got your hydrogen here, you've got your helium over there, and you got this empty space. All of these things are in this place because they have a pattern. This is like this. This is like this. So, since this is like this, is like this, and this is like this, is like this, you've got something here that's probably like that. And then maybe there's another row above it. And if you're thinking about stuff like this, then you have to also recognize about how light works. Light is a wave. Waves need a medium to transmit through. You hear the waves of sound coming from me because the air is moving that energy. So light is the same way, or at least in the 19th century they thought light was that way. It needed something to travel through. They called it the ether. Something that was very, very small, but mattered. These subhydrogen elements. The ether. So, the thing is, it doesn't exist. We all know that. Michelson-Morley experiment of 1887 proved that it did not exist. Or at least it could not find, it couldn't find any evidence for it existing in the way that the theory said it should. Basically, they had tolerances. It should be to, like, 3 decimal places, and they should be able to find something there. Well, they took it out to a couple more decimal places, and they couldn't find it, so it doesn't exist. But that didn't stop other people from still using it. John Worrell Keely. John Worrell Keely is a name you want to remember. If you're doing steampunk stuff, he had this thing. I love John Worrell Keely. Here's a story. This is actually, I read this on a posting on the internet. In the 1880s, John Worrell Keely flew a piloted sympathetic harmonic propelled craft over the U.S. War Department in front of more than 800 government observers who afterwards had the vehicle stored in a limestone caverns located beneath the University of Florida in Gainesville. Apparently, the famous financier named John Jacob Astor, you recognize his name, was set up to be on the was funding the research by John Worrell Keely. And he was set up to be on the Titanic. He was lured to bring on board for shipment an array of newly built Tesla technology devices, including Tesla transmitting technologies that would have provided regional electricity in unlimited abundance. We all know what happened to the Titanic. It was a grand conspiracy to destroy free energy. Yeah. But the actual history of John Worrell Keely was that he built this machine with magnets and spinning bits and tuning forks that would drive a motor using etheric gases. Basically, he would take a violin bow and he'd set these tuning forks a-going, and he'd put some water in there, and the water would break down into its etheric elements and drive this motor. And he was trying to sell it, and he got people to fund him for a long time, and he was convicted of fraud, and he still kept doing it. And only after he died did they go to his laboratory and tear it all apart and find a little hose that ran from the table to the pressurized air cylinder in the basement to run his machines. Everyone knew that he was fraud. But to this day, there are people who believe that, yes, John Jacob Astor and Nikola Tesla and all of them were on this conspiracy, and he was right all along. You can go online and you can find these people who believe that he built these spacecraft. And Tesla, let me find that quote on Tesla. I got to talk about Tesla. Let me see here. All right, so here's this thing, Wall of Light. So here's a website. First sentence. Tesla always claimed to be a Venusian. Okay, I'm not going to read anymore. No, he didn't. I've read Tesla's work. He doesn't claim to be a Venusian. I don't know where they got that from. They're just making stuff up.
Wasn't he Serbian?
Yes, he was Serbian. He was a Serbian Croat or a Croat. I think he was a Serbian Croat. So he was in Croatia, but he was Serbian. Something like that. Yeah, so that's all we're going to talk about with Tesla. But again, in a way, that follows from the 19th century electric machines, the anti-gravity that was so popular in the 19th century. What is the time? I'm doing this. I'm on this. Okay. I want to mention one more thing. It's a story called Dr. Omega. This is written in 1905. French story. Let's see. So in this story, he has this material, stellite. Stellite? Stellite. 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 I don't know, it's translated from French, so who knows what it is. Drawn from a black hole. So you take this material and you pull it out of a black hole. Now we all know black holes are weird. They don't exist as part of our universe. So if you take material out of a black hole, it wants to go back to its universe. So you can use that to travel within the universe. So he built this machine. Oh yeah, stellite drawn from a black hole, a pan-dimensional metal that will not naturally remain in our natural universe, a living metal not part of the quadridimensional structure of space and time, thus repels them. So this guy, Dr. Omega, has a machine that he can travel through space and time. And he's an old guy, you see his picture here. Wears a fur hat and a scarf, and has a granddaughter, and travels through space and time. Omega is the symbol, electronic symbol for ohm. It's an electronic thing. But if you turn it upside down, so Dr. Omega is Doctor Who. This was 1905 when Doctor Who was written, but probably not really. What I think really happened, and I'd like to see a better translation, is there are some parallels within this story of Dr. Omega between this good doctor and Doctor Who. Some parallels. And when the translators took the original French stories and translated it in English, they didn't just translate, they adapted. So they put references to Doctor Who to make him seem much more like the William Hartnell Doctor that we know. It's still an interesting story. For example, when they say black hole, 1905, black hole was not part of the lexicon. Not at all. All right, so I've rushed through a lot of stuff. I've got a few more minutes. So yeah, I've got 10 minutes. So are there any questions you want to ask about other 19th century spacecraft or other ideas? If you're writing your own stories, do you want to talk about how you can make your spaceships fit this kind of 19th century aesthetic of how things worked? Yes? Compressed air. Compressed air is great. We use compressed air in spacecraft today. Well, not compressed air. They usually use hydrazine, I think. Hydrazine it's a liquefied gas that will expand, and it expands better than air does. So they use that for their
You're somewhat incorrect. It burns by itself.
It burns by itself.
Yes.
So as soon as it's, I guess, and it's a pressure thing. Once the pressure rises above a certain thing, it ignites. Is that how that works?
I think
Or
if you
lowers.
I think if you vaporize it and then ignite it, it has its own oxidizer as part of the molecule, so it will burn
now I know that.
by
Okay,
itself.
so that's one method, but I think there is another.
They do use in some cases, I think, compressed nitrogen gas.
Just nitrogen,
Very
which is pretty much air.
One of the SpaceX devices was using a compressed air for part of the thing, but they didn't have enough in it, so it had a problem. But
Their reaction control thrusters at the top.
It was hydraulic fluid.
was it?
Yeah, it was
Yeah, they had a
hydraulic
problem with hydraulic fluid, but I think he's right. If you know about SpaceX, SpaceX is a private company building spacecraft, and their Falcon 9. So basically, you've got yourself a rocket, and they throw some landing legs on the bottom. So they launch this up into space with their capsule. They disconnect the capsule while they've still got fuel. And then this thing falls down. They got some wings up here, or some spoilers to help slow it down and guide it. And then with that little bit of fuel they have left, they turn that rocket on right at the last minute and they land.
Or try.
Or they tried to. They've had 2 failures yet, or 2 almost successes.
It hit the platform.
It hit the platform, yes. They nailed the platform twice. And
So they lost the platform and the rocket.
no, the platform's pretty, yeah, got it. Okay, so at the top, they have reaction control thrusters, which, and I think you're correct, they are just using like a compressed gas of some sort. They aren't using like a rocket engine of anything, or the hydrogen that ignites, or the hydrogen that ignites. I think it's just compressed whatever gas it is. And to hear people talk about it, it's like they don't think it's quite enough to really control it. But the thing is, it doesn't need to do a lot of control because this rocket engine is vectored. So this rocket engine will turn back and forth to push it from the bottom and keep it upright. You could see it when it came down. It came down and it started to do this, and you could just see that nozzle turn and just kick the bottom over to the other side.
Yeah, the reason it has to do that is I think it's so it doesn't burn from the bars by going straight down. Is my understanding.
Well, no, it really is the most efficient way to do it is to burn at the last moment. There is a game out there, and they're going to release their brand new version on Monday called Kerbal Space Program. I see you smiling. Kerbal Space Program. It does all this stuff. And I have flown these rockets, and I know how they behave. You'll know more about rocket science from playing Kerbal Space Program than from anything else you could do,
So this is
aside from working for NASA.
This is a trainer this company has put out to get future pilots, right? Is that it?
Kerbal Space Program. It's a game. Kerbals are like these little green guys with big helmets.
They're telling you it's a game.
They're telling you it's a game, but they've got a whole lot of math in there, and they do the vector thrust, they do the RCS, they do aerodynamics. It's fantastic. I have an older version that I run. I can't run the newer version because it doesn't work on my machine. But the new version comes out on Monday, so go get it. There is a steampunk patch for it. So you can have steam-powered rockets. And you can make airships, dirigibles. I don't know if they do ether anti-gravity stuff, but I'm pretty sure they've got that. Any other questions? Okay, so tomorrow at 11, I think in one of the rooms over here, I am doing a presentation on H.G. Wells and the War of the Worlds.
11.
His magnum opus. I think it's 11 o'clock.
11 a.m. I'm assuming.
11 a.m., yes. So, War of the Worlds, I'm going to talk about that. And then on Sunday, I don't know exactly when, but I have a presentation on Sunday on the hollow Earth.
Cool.
We all know that there's a big empty space underneath the Earth, right? Mm-hmm. Yeah, sure we do. Okay. Anyway, I want to thank you all for coming. I want to thank you all for staying. And hope you enjoy the rest of your convention. Yay!
Hollow Earth at 1 o'clock in the Milan room.
Oh, okay. See, I don't even know. It's on the program, and I'll check the program before I do it. But
Fill out one of these surveys over here. Grab one of these.